So in Calculus 1, we learned that the integral of 1 over square root 1 minus x squared dx was arc sine, and that integral of 1 over 1 plus x squared dx is arc tangent. And the way we obtain those integral or those antiderivatives was the way we obtain those antiderivatives is through the method of trig sum. And the idea behind trig sum comes from using or involves using our Pythagorean identities. So let's start with this first example. So notice that if we start with our identity sine squared theta plus cosine squared theta equals 1, if we move sine over to the right side, we get cosine squared theta equals 1 minus sine squared theta. And notice how this looks a lot like 1 minus x squared. And so if we were to make the substitution x equals sine of theta, in which case dx equals cosine theta d theta, we can go ahead and make this substitution into our integral and see what happens. Notice that this is different than the method than our normal method of substitution, in which we have u equals some function of x. Now we're making x some function of theta. And so in this case, what happens when we substitute in what we have? So wherever we have an x, we're going to replace that with sine. And so we'll get integral of 1 over square root 1 minus sine squared theta. And wherever we have a dx, we want to replace that with cosine theta d theta. So we're going to get a cosine theta d theta over on the side here. We can bring the cosine up into our numerator to make things look a little nicer. So we get integral of cosine theta over square root. Now, notice that 1 minus sine squared we have up here as cosine squared theta. So now we see the benefit of making the substitution. And we're taking the square root of cosine squared, which is going to give us a cosine in the denominator, theta. And notice that the cosines cancel. So we get the integral of d theta, or theta plus c. Now we're not done yet, because we still want our answer to be in terms of x. In this case, we know that if x is sine theta, then theta is arc sine of x. And so, for our final answer, we should have arc sine of x plus c, which is exactly what we know from Calculus 1. By a similar method, we can verify that the integral of 1 over 1 plus x squared is arctangent. And in this case, the Pythagorean identity that we want to use is the fact that 1 plus tangent squared theta equals secant squared theta. And once again, notice that we have our 1 plus x squared here, and we have 1 plus tangent squared here. So the logical substitution make here is x equals tangent of theta. And just like we did in our first example, we need to take the derivative of both sides. And remember that the derivative of tangent is secant squared theta, d theta. And so we've got our substitution here. And just like in the first example, we're going to substitute, everywhere we see x, we'll substitute in tangent. And then where we have dx, we'll substitute in secant squared d theta. So the integral of 1 over 1 plus x squared dx equals the integral of 1 over 1 plus tangent squared theta, and then dx we said is going to be secant squared theta d theta. And just like we did in the last problem, let's go ahead and rewrite this a little cleaner. Also notice that 1 plus tangent squared theta we say is secant squared theta. So our denominator will simplify to secant squared theta, d theta. And just like in the first example, we'll have a little cancellation, in which case we get integral of d theta is theta plus c. And once again, we're not done yet. We still have to get our solution in terms of x. And we know from our original substitution that theta equals arctan of x. So our final answer here is arctan x plus c, just like we expect from Calc 1. Finally, let's do this example for 1 over the square root x squared minus 1. So we're going to borrow our same Pythagorean identity that we had in example 2, but we're going to rewrite it slightly differently. So we're going to move the 1 over to the right-hand side so that we get tangent squared of theta equals secant squared theta minus 1. So notice that secant squared theta minus 1 looks a lot like x squared minus 1. This is our intuition behind the substitution we want to make. So where we have x squared, we want a secant squared. So the substitution we'll make is x equals secant theta. And the derivative of secant theta, recall, is secant theta tangent theta d theta. So in this case, when we do our integral, we get integral 1 over square root x squared minus 1 dx. And we're going to substitute in x from the x and dx at the very end here. And for simplicity, I'll move the secant tangent theta up into the denominator, kind of like what we did in the previous examples. So we get integral of, so dx will turn into secant theta tan theta d theta. And in the denominator, we get square root of secant squared theta minus 1, just like what we wanted up here in our Pythagorean identity. And so we get the square root of tan squared theta, or secant theta tan theta over square root the tan squared theta d theta, and this is equal to the integral of, so the square root of tan squared is going to be tangent, so the tangent and tangent down here are going to cancel and simplify, and we'll integral of secant theta d theta, and Well, but you said this, right? Yeah, yeah, what is the equal secant? Right, it's, right, so the equal secant we know is, the actual log of absolute value of secant theta plus tan theta, plus c. And at this point, we're not done, because we still want our answer in terms of x. And so, what we have to do is we have to make our right triangle, just like we did in part 1. So we know that secant theta is x. So we have hypotenuse over adjacent. So we get x over 1. So then our opposite side is going to be square root x squared minus 1. And so secant theta is going to be x. And tan theta is going to be opposite over adjacent, or plus square root x squared minus 1 plus c. Yeah, that's it, I think. Yeah.